Okay, so now we're going to look at energy conservation when two or more objects interact. Situations in which we're looking at two or more objects involve things such as an Atwoods machine or collisions. As you recall, we discussed collisions when we talked about conservation of momentum. So, with a single object, we can explore the conservation of mechanical energy as that object undergoes changes in its position. In this diagram here, the snowboarder starts with 50,000 joules of gravitational potential energy and ends with 50,000 joules of kinetic energy. At various points along the way, the distribution of that energy changes, but the total energy remains constant. Of course, this is for a frictionless system. If we include friction, we're going to see changes to this total amount of energy due to energy being transferred to the environment. And we often hear or talk about energy losses. Now, it's important to understand that energy is never truly lost or destroyed. It's just transformed into some type of energy, such as thermal energy, that's not easily recovered. And we call this the first law of thermodynamics, and we're going to cover that in more detail later on. Okay, so now let's look at the energy involved in an Atwoods machine. We've seen these previously, and we used Newton's laws at that time to describe the dynamics of such a system, but we can easily apply conservation of energy concepts to them as well. In the Atwoods machine pictured here, we have a 2 kilogram mass 1 and an 8 kilogram mass 2, where mass 2 is 2 meters above the ground. When the system is released, we want to find out, say, the velocity of this system just before mass 2 strikes the ground. Now, if we were looking at this with the tools we've previously used to explore Atwoods machines, we'd have to do a bit more calculation. But as we're going to find with energy concepts, it becomes much more simplified. We're going to start by recognizing that the energy of this system will be conserved. My initial energy will equal my final energy. So we can write down the possible energies we're going to have before and after, and then decide which energies we truly have, and which ones we don't have. So since we start from rest, we know that there is no initial kinetic energy, so we can get rid of that. And we start with only the gravitational potential energy of mass 2. Mass 1 does not have gravitational potential energy. So right before mass 2 hits the ground, it has all kinetic energy, and mass 1 has gained gravitational potential energy. But mass 1 also has kinetic energy because it too is moving. So at the end of this, we will have gravitational potential energy and kinetic energy. So my initial gravitational potential energy is due to mass 2. At the end, it's going to be mass 1 that has that gravitational potential. Now let's take a look at this kinetic energy. At the end of this system, both of these are going to be moving. So we're going to be looking at this just before mass 2 hits the ground, and therefore just before mass 1 comes to a stop up here. So because both blocks are going to be moving with the same velocity, we can add their masses to our equation for our final kinetic energy. So this is the energies that we have to work with. So when we go to plug in numbers into this, we've got our 8 kilogram block here, a 2 kilogram block here. It moves down 2 meters. This one moves up 2 meters. And we end up with a final velocity then of 4.85 meters per second. That's the velocity just before striking the ground. Okay, so now let's go ahead and move on and look at collisions. Okay, so we've previously talked about collisions. We talked about elastic collisions and inelastic collisions. In elastic collisions, objects collide and bounce away from each other. In inelastic collisions, they collide and stick together. In all types of collisions, momentum is conserved. Okay, but energy is not always conserved. In an elastic collision where the objects collide and bounce away from one another, in those collisions, both momentum and energy are conserved. In an inelastic collision, when objects collide and stick together, momentum is conserved, but kinetic energy is not conserved. The reason it's not conserved is due to all the frictional forces that occur during that collision. A lot of the energy then is transferred off into the environment as thermal energy during that collision. Okay, so let's go ahead and take a look at an example that shows this. Okay, so here we have two air track gliders, and they're going to have a collision. One of them is moving to the right at 3 meters per second. The other is moving to the left at 2.25 meters per second. And they have different masses. They're going to collide and stick together and move together with a final velocity of 0.5 meters per second squared. We want to compare the initial and final mechanical energies of this system. So let's start by looking at the kinetic energy of the entire system before the collision. So before the collision, object mass 1 is moving to the right at 3 meters per second. Object 2, mass 2, is moving to the left at 2.25 meters per second. So we're paying attention to the direction there. And we end up showing that we have an initial kinetic energy of 1.91 joules. So then after this collision, we want to see what changes happen to this energy. Because the gliders stick together and move as a single object, the final kinetic energy is 1/2 the sum of the masses times the square of the final velocity, which works out to a final kinetic energy of 0.075 joules. So what this means is that for this particular collision, we have a difference of 1.84 joules of energy that's been released off into the environment as thermal energy. Okay, and that comes about because of the friction involved in that collision. So about 96% of the initial kinetic energy is actually transformed into thermal energy, which is really kind of typical of most real-world collisions. Okay, so what we really need to understand about energy in collisions then is that in an elastic collision, momentum and kinetic energy are conserved. In an inelastic collision, only momentum is conserved. Kinetic energy is not conserved in an inelastic collision. We'll look at examples and see problems of both types of collisions in class. We'll see you then.